Okay, so let's get this thing out of the way. All right, so last time we talked about phenomenology, and we talked about why phenomenology is for a physicist not a bad thing, why it's a good thing, and in fact why I didn't say this, but it's true. Everything we do in physics is phenomenology or in science, because in phenomenology, as we discussed, what we're doing is trying to make some intermediate scale description of a system, and we use symmetries and conservation laws and analyticity and things like that in order to make our mathematical models, and they always have parameters in them which involve lower levels of description. So we derived from Navier-Stokes equations, and we derived and we saw that there would be, you would guess that there should be a term like this, which is rotationally symmetric and involves a derivative of v and is analytic. And so we have to introduce some new parameter which somehow absorbs all the information at lower scales. And that was the Navier-Stokes equations. And then we talked about, well, is that derivation, is it hand waving or is it more profound? And so we said, well, you could do a more microscopic calculation by doing scattering theory. So here I've written down some diagrams that tell you about scattering theory, and one can indeed do scattering theory, and one can derive this equation by taking the equations for this and taking the second moment to work out the expectation value of velocity, and so you can derive this equation. And moreover, in terms of the parameters of the scattering cross-section, for example, you can write down a formula for what this eta is. And that was done by Maxwell already in the 1860s or something, and Boltzmann in a more systematic way in the 1890s. And so the direct calculation confirmed the general form of what we guessed from analyticity and symmetry and so on, phenomenology, but also provided details about what this thing actually was in terms of the cross-section of the particles. Now, then we talked about why phenomenology is better, and the reason phenomenology is better is because it has a larger range of validity. Scattering theory is restricted to dilute systems, and phenomenology is not. So scattering theory will describe a dilute gas. The Navier-Stokes equations describe fluids, all fluids in the universe that we know, and so it has a much greater range of validity. Now, you could say, well, of course, the Boltzmann equation version is much better because we actually have a formula for eta in terms of the scattering cross-section of the particles as they bounce around in the box and bounce off each other. And you can do that classically, or you can do that from a quantum mechanics. You might say that's a microscopic derivation, but it's not, because you can say, well, where did that scattering cross-section come from? Well, that came from the mass of the particles, the charge of them, the size, and things like that. And where does that come from? Well, that comes if they're atoms, it might come from nuclear physics or atomic physics. So there's all sorts of quantum mechanics and so on that we've taken for granted in just writing down the kinetic theory in terms of scattering cross sections and so on. And of course, you can say, well, I can make another theory that gives me those formulae. And you can. It's called QCD and electroweak theory standard model. It has 26 adjustable parameters, and you can fit those by experiment. But then, of course, where do those parameters come from? So basically, every time we write down theories, we're using phenomenology. Now, the next thing that we learned last lecture was we talked about how you can apply this to looking at ordered systems. And what we talked about at the end of the lecture very quickly was that if you write down systems that have continuous symmetries, and I've given you examples in the lecture, it turns out, and you'll do this in the homework problem, it turns out that they have no long-range order in 2 dimensions. So if I've got a continuous symmetry, let's say an XY model, it will not order, at least it seems that it will not order in two dimensions, except if you have topological order, and that's a different thing. Now, we talked about that, and then I gave you the example of a swarm or a flock. So in a swarm or a flock, I have some fish or some birds or something. They move around, they have a vector, which tells you which way they're going, and they're following maybe the person in front of them, or the fish, or the bird in front of them, and they're doing some behavior, and the whole flock does some very magical, beautiful behavior. And so we can describe the flock. We can look at it at the level of each individual bird or each individual fish, but that's kind of overkill. We just see, we look up in the sky, each bird or fish looks like well, it's a bird if it's in the sky. Each bird looks like just a point particle just moving around. So I can coarse grain the velocity on some scale larger than the mean separation between them. I have a continuous velocity field that describes the flow of the particles as they make their swarm or their flock. And what I told you was if you do that, you get an equation that looks like the Navier-Stokes equations. So here is the here are the equations. So these equations, if you look at this, dv by dt, v dot grad v, I derived that term for you in class. Then there's various other terms here which you can see. So you can see that these equations are kind of like the Navier-Stokes equations, but they have extra terms in them that are meant to describe the fact that these things are self-propelled and that they orient based on their neighbors and so on. Now, what do you find from these equations? And these equations were first written down by John Turner and Yu Hai Tu about 25 years ago, slightly more. What they found is that in two dimensions, they can spontaneously break symmetry, meaning that they can all flock and everybody's flying in some unified direction, rather than what happens if you take a carload of physicists and you drop them off in the car park outside of some shopping mall, and you all go in random directions. Okay, that's what happens with physicists, but birds and fish are more intelligent, and they all swarm along together, and that would seem to break that ordering would break the Mermin-Wagner theorem, the fact that there isn't order in 2D. It turns out that there is if these systems are out of equilibrium. So that's how we that's what we did last lecture. So today I want to now apply this to Landau theory. So we're going to follow the discussion in my book. So we're going to now discuss phenomenological Landau theory. And this is recording, right? This word dot means it's recording, I guess. I think I hit the record button, didn't I? Yep. Okay. Okay. So let's write down phenomenological Landau theory. So our goal here is to develop an argument based on symmetry and analyticity for the generic form of the coarse-grained free energy. So in the course that some of you took last quarter, we actually derived this form starting from mean field theory from a particular model of the Ising model. But here we're going to just see that this can be done from top down. So last quarter, in that course, we derived this in a bottom-up way from the Ising model. So we literally calculated this, and so now what we're doing in this section is what I'd call top down. We're just going to look at the general principles. So let's start off by saying that we think of the system as having various coupling constants, and what a coupling constant is which I'm going to call K sub I. These are just the parameters that you vary in the laboratory in order to control the physical system. So let's suppose I've got a magnet, then I might be changing the temperature. If I've got a magnet in an external magnetic field, I'd be turning the magnetic field up. If I was tuning the couplings between the spins by changing some electromagnetic field abating the system or something like that, that'll be another knob like a term. So all these coupling constants are some parameters that we will call Ki, and we are looking in terms of an order parameter, which I'm now going to call eta. And so this order parameter, an example of this would be the magnetization in a magnet. So the magnetization per spin. So that could be, for example, eta is 1 over n, the sum from I equals 1 to n of the thermal expectation value of all the spins. So that would be an example of an order parameter. Later, we could write down a much more complicated order parameter. And last time we talked about the order parameter for a vector magnet, like a Heisenberg model, an XY model. And I also told you that this can be a much more complicated object. In the case of helium-3, it's a very complex matrix order parameter with which is a representation of SO3 cross SO3 cross U1. And so it's a very complicated 18 parameter. Okay, but anyway, so we're going to call it eta. And so what we're going to say is we're going to construct the Landau free energy and what does L tell us? Well, last time I wrote this down. Let me just go back and remind you of what it tells us. So here it is at the top of the screen. So we started off with our microscopic statistical mechanics, the scale of a lattice, if we're talking about a solid state physics system, for example. At the larger scale, the system size, we look at the thermodynamics of the 19th century. And then the 20th century, after about 1960, is this. So we take some coarse-grained description of the system, and then we have some order parameter psi, which varies slowly in space, and we want to know what is the free energy associated to that. So maybe I should just take this out. Okay, maybe I shouldn't. You can all see it. So here is our microscopic picture. So a microscopic picture in the case of, say, Ising's model would be spins that point up and down, something like this. And then, so this would be the SI in one dimension. The eta would look something like this. So I could make a coarse-grained version. So my coarse-grained version So what do? Is I take this configuration. Let's say I take a sliding window which in this case has got five spins in it. So I'll call this a sliding window. And I measure the magnetization per spin in that. So this one is up, down, up, up, down. So it's 1, minus 1, 0, 1 plus 1, 2, minus 1 is 1. So this happens to be 1, but there's 5 spins there. So the magnetization in this little area here, this magnetization per spin in this thing, the M of this window is 1 over 5. And then I can just take this sliding window, move it along the x-axis like this, and then I can make up a graph of this m lambda as a function of distance, and that will look something like, I don't know what it will look like, but something like that. And the point is that it's going to look like this is going to be a continuous smooth function. And we like continuous smooth functions because we can use calculus for that, so that's good. I've indicated here this lambda here. This lambda is the width. So this lambda is equal to 5. So of course, if I made the window, a million, well, then obviously I'm not going to have very much spatial variation at all. If I make it 1, then I'm just into this situation. At this level of description, at this microscopic level, why I don't like this function is not a function. Okay, the magnetization is discontinuous. And not smooth, and that's bad. So we want to zoom out a bit, have a coarser grain level description, and so this is the configuration of the system. So after we've done this, we have a function m lambda as a function of space, and that is the equivalent, the coarse graining of the spin at each site I. So now I have this as a continuous function of space, and that's the important thing. And then the question that we want to know is this question: what is the probability of observing the system with a given coarse-grained magnetization? I've used m here, but this m is what I mean by eta. So that's what it would be in a particular example. We want to know what is the probability of observing that. And so when I ask what is the probability of observing the system at with a particular configuration of the spins, a microscopic configuration, we know that that is equal to e to the minus beta times the Hamiltonian divided by the partition function. And the partition function is just a fancy name for the normalization. So we sum over all the degrees of freedom, e to the minus beta times the Hamiltonian. Okay, so that's what we do in microscopic statistical mechanics. Now, so by analogy, we can say, well, what's going to happen when I coarse grain the system? What's going to happen for the probability of observing the system with a given coarse-grained magnetization as a function of space. So that is going to be given by e to the minus beta times this Landau free energy, and now depending upon m lambda of x, like this, and normalized by the partition function. And in this particular case, the partition function is the sum over all functions in space of e to the minus beta L. And how we do this sum over functions, that's called functional integration. And don't worry about that because it's easy. So we'll talk about this. So the precise way you do this is a technical point that we'll come to later. Precise definition in terms of Fourier components. But this is my sort of notation, at least for now, for what is known as functional integration. And if you want to skip ahead in the book and learn what that is, that's the buzzword that you want to look at. Okay, so we'll just assume that we can find a way to solve all possible random functions like this, and we'll talk about that. And then if I know, just by analogy with what we have with the Boltzmann distribution, we know that we've got a free energy defined at the coarse grain scale. So we also expect to have Boltzmann distribution and the probability given in this way. And so our question is, how do we construct the order parameter? How do we construct this Landau free energy as a function of its order parameter? And that's the question, and our answer is to use phenomenology. Okay, so let's go ahead and do that. So there's going to be several principles that we're going to use. When we talked about deriving an Navier-Stokes equation, we said, well, the system's got to be translation invariant, it's got to be rotationally invariant, it's got to have some term that involves gradients, and it has to have, encapsulate the conservation of momentum, so we have F equals ma. So that's how we constructed it. So we need some of the principles that enable us to construct L. And now I'm going to use eta because this applies to any system. So we're going to be using eta rather than m. So first of all, we have the order parameter eta, and for now we'll assume that it does not depend on space. Okay, then I'm going to add space afterwards. Okay, so that's the first thing. So then L has the interpretation of some sort of free energy. And so what that means is that the state of the system i.e. the value of L, sorry, the value of eta, is given by extremizing, or minimizing, in fact, L. So what we know is that dL by d eta should be equal to 0, and this equation will give us the value of eta as a function of the coupling constants, in particular temperature, magnetic field, and so on. So that's that's the idea. Okay, so that's the first thing. So now let's list the desiderata. Desiderata means the things that we desire. So the first thing is we want L to reflect the symmetries of the system. So by symmetries, I mean, say, up-down symmetry, if it's an Ising magnet. If it's a XY magnet, it would be the rotational symmetry and spin space and so on. So that's going to be the symmetries of the problem, which can be space-time symmetries, like rotationally invariant, or they can be order parameter symmetries, or spin symmetries like the ones we talked about last time. Then we are going to assume that we can expand L in a power series about eta equals to 0. So the real reason that we think we can do this is because we're thinking that originally this was worked out to describe the system near a critical temperature. So let's suppose I've got temperature here, and I'm measuring the magnetization per spin over here. Then what we know happens is that the system has no magnetization above some critical temperature, and then below some critical temperature it rises with some exponent, and eventually goes to 1. And what we did last quarter was we developed a theoretical understanding of exactly what happens here. And in fact, we saw that M goes like Tc minus T over Tc to the power beta, where beta was about 0.326 or something like that. But so here, the order parameter is small, so therefore you say, well, then we can expand in the power series. And what we hope is that at least we can capture the nonlinearities or the behavior, the things that cause this thing to saturate. So over here, this saturation or it should be captured by our power series expansion. Okay, so that's the first thing. So in other words, what we have said is that L of eta is an analytic function of eta. So that's the first thing. So let's suppose that the system is spatially uniform. So if we assume that it is spatially uniform, just for now, and what that says is that L is going to equal the volume of the system times the Landau free energy density. And this L, by supposition, is equal to the sum from n equals 0 to infinity, some coefficients that may in fact depend on the coupling constants and will depend on them, times the order parameter, and then we're going to sum in raised to the nth power. Okay? So that's the general form of this. And then later, in a few minutes, what we will do is later we will add a term to allow spatial variation so that eta becomes now an eta that depends on space. Okay, but for now, let's just keep it spatially homogeneous. And then what do we need? Well, we need the following in the disordered phase of the system, i.e. temperature above the critical temperature. We know that the order parameter has to be equal to 0. And then, so that must mean that eta equals 0 is the solution of dl by d eta is equal to 0. So that's going to be true. And then in the ordered phase, i.e. t is less than tc, eta will be non-zero, and that will have to be a solution of the extremal equation as well. So that's the first thing. What we're also going to do is, for now, we will assume that we are near Tc. Eta is much less than 1, and so we truncate the expansion. And where do we truncate the expansion? We truncate the expansion at n equals 4. So we're going to just do this sum, not to infinity, but to n equals 4. Now, why n equals 4? Because for this particular problem, n equals 4 turns out to be sufficient to give us the shape, the qualitative behavior of the system. There's other systems where you have to go to a sixth power and so on, for example, tricritical points and so on. So, but this truncation of the expansion, this will be sufficient to capture the general behavior. So the general behavior that we're trying to capture is this behavior here. We have the onset of order, then the order saturates, and just by expanding up to the fourth order, we will be able to do that. So that means that we can now write down the general form. So L is going to look like this. Going to sum from n equals 0 to 4, an that depends on whatever the coupling constants are, times the order parameter raised to the nth power. So now let's construct it. So let's first of all apply the extremum principle. So the eta minimizes L. So what we have to do is look at the equation for dl by d eta. So what is dl by d eta? So it's a1 I'm summing here from n equals 1, but n equals 0, but I really want to sum from n equals 1. Correct that typo. So I get a1 plus 2 a2 eta plus 3 a3 eta squared plus 4 a4 eta cubed, and that has got to equal 0. Why do I only sum from 1 to 4 rather than from 0 to 4? Why did I change that?
That constant would be the same for all values of the order parameter. It would factor out the partition function.
Exactly. All that would do, the e equals 0 term, so the n equals 0 term means e to 0, which is just 1, so it's just a constant. So that's just redefining the 0 of energy. So we don't care about the 0 of energy. So the reason we have n equals 1 to 4, not n equals 0, is that the n equals 0 term can be set equal to 0 because it is just a redefinition of the 0 of energy. I should have done that in a different color. So I'll put a box around it. So there it is. So that's the reason why we don't need it. So that tells us this. Now what we want is for t greater than tc, we need eta should be equal to 0, and that has got to satisfy this. So that immediately tells us that A1 must be 0. Yes.
In your sum, is it eta to the n minus 4? Or, oh no, never mind.
I differentiated. Yep, I differentiated. Okay, so the first term, the linear term, has to have, this coefficient has to be 0. If not 0, I will not get a solution. Eta is equal to 0. This equation has to be satisfied. T greater than Tc, eta equals 0 has to be a solution. It won't be a solution unless A1 is equal to 0. So we have to have that. That's the first thing. Okay, now let's look at symmetry. So let's suppose that we are looking at an Ising system with h equals 0. I've got a bunch of spins that can point up or down. We know that the Hamiltonian doesn't change its energy if I flip the sign of the spin. So we know then the Hamiltonian is an even function of the spins, and therefore the thermodynamic free energy, and indeed the coarse grained free energy, has to be an even function of eta. So that means that the probability distribution for eta should be the same as the probability distribution for minus eta, and so that means that L must be even. Because the probability distribution is just given by the Boltzmann factor of e to the minus beta L. So given that it is even, then that tells us that A3 equals A5 equals A7, etc. All of the odd terms are equal to 0. So we start off with this Landau free energy. Actually, virtually every term is 0. So let's see what we have left. So that means that we have left then that L is equal to some 0 free energy, then A2, which can depend upon the coupling constant, whatever they may be, can depend on temperature, eta squared plus A4 times e to the 4th. So that's the structure so far. We can do more than this. Question for you. Why is there another term that is linear in eta that I could add here and would still be even? Can anybody think of a term that I could have added here that would still be an even function, but is linear in eta? I could have had absolute value, exactly. So notice a term like this is absent. Why? why do I not have that term in this formula? So I've told you the answer, and the answer is even on the blackboard. I don't know what this thing is called.
So the same argument as before that you can eliminate it with the z. The way it gets normalized out.
No, it wouldn't be normalized out. I mean, if I had the A0 term here, that would just be cancelled top and bottom in the probability distribution. So the zero of energy doesn't make any difference. But this is something to do with the order parameter itself.
It would correspond to the A1 term.
Right, but that
It's not analytic.
yes, it's not analytic. Okay, I could have had such a term, and I had to worry about it, but it's not analytic. Why do I need it to be analytic? What tells me that I have to use the constraint of this being an analytic function in order to do this? Yeah, I'll help you. Let's remember physics of what we're doing. Here's the physics of what we're doing. Okay, we're making the system, we're taking a sliding window and we're coarse graining our order parameters, moving along. Okay? So what I'm calculating is the coarse grained, the energy that gives rise to this as some expectation value. So what do you know about this thing? Think about what we were doing last quarter when we were doing the kind of block spins and things like this. What do we know when we're formally constructing this? Okay? Some of you will know from what we did last quarter, but you can also understand it intuitively just by looking at this cartoon. Remember, at the root of everything that we're doing sums of e to the minus beta h, right? Right, everything we're doing is sums over degrees of freedom or Boltzmann factors. Okay? When we construct these sliding windows, how many terms of e to the minus beta energy are in each window? Five. In this example, the one I had on the screen, I had 5 terms, right? So when I'm computing the expectation value of n at this point in space, I'm computing the sum over all the possible configurations of these spins here. 5 spins, so it's a finite number. So I'm adding up 5 values of e to the minus beta times the energy. So that has to be an analytic function. So I can't have any terms in this Landau theory which are not analytic. So the answer is that we are coarse graining over a finite window width. And so that implies that everything is analytic. The function absolute value is not analytic. It's a function that looks like this. And it has a slope discontinuity here, so it's not an analytic function. So I can't have that. There's no way I'm doing this in a principled way that I could generate such a term. Okay, so then next constraint. A4 has to be greater than 0. Why do I know that? Well, one of the things about energy of a physical system, free energy, is it has to be bounded below. Because otherwise, if I'm going to minimize the free energy, if this term, e to the fourth has a negative thing here, and the free energy looks like a curve that goes like minus e to the fourth at large values of eta. So I can always minimize the free energy by making E2 equals infinity. Well, that doesn't make any sense. The energy of a system is bounded below, so A4 must be positive. So now we know what that is. Okay, so A4 is positive. So we can just say that A4 is some pure number. Okay, now so we've only got one term left. Okay, I told you we're going to find a general theory for everything. This is the theory of everything, and it's only got one parameter in it, A2. Well, what we want to have happen is that as we go below the critical temperature, the system orders. So what we want is that below T less than Tc, we want eta to be non-zero. So let's have a look at our equation, dl by d eta. So A1 is equal to 0, so this is just 2A2 eta. The A3 term is gone, and then I've got 4A4 e to the fourth, and this is equal to 0. And what we want is that for t greater than Tc, we want eta equals 0 is the only solution. Eta cubed, yeah. Thank you. Is the only solution, and so that will happen. We'll only get that if A2 is positive. For t less than Tc, we want eta to be non-zero to be a solution. And the way we can do that is if A2 is negative, then what I get is that minus A2 over 2A4 is equal to eta squared. That would be a solution. So that has to be non-zero. And so what that tells us is that A2 changes sign at Tc. And so what we can do then is we can say, okay, fine. So we'll write that A2 is equal to some A2 0 plus a A2 1. And now I'm doing a Taylor series expansion in temperature. Etc. So I could expand that as a function of temperature. And then what we know is that this has to change sign. So it has to change sign. Then this term must be 0. So in order for it to change sign, that means that A20 must be equal to 0. And if we're near Tc, or near enough to Tc, then we neglect higher order terms. And so now what we've got is a very simple description of everything. So now we have that our Landau free energy density is just some number times little t times eta squared plus 1/2 b e to the 4th, and that describes the system. So this little t here is defined to be t minus tc over tc. That changes sign as I go below the transition, and this b is what I called a4 before. Now for this part of the course, I've written it down as just a half b. It just seems to be the normalization I used when I wrote this book, and this is our formula. If we had a coupling to an external field, what we would say, well, we know that an external field couples to the system by a linear term. There's our microscopic interaction. And now if I add an external field, that comes in like that. And so therefore, what that will do is in the Landau free energy, this will give us L is equal to a t e squared plus 1/2 b e to the 4th, and then I'll have this this term h times eta. And so a and b are just numbers. This is number greater than 0. This is number greater than 0. So they're phenomenological parameters. And this is our picture of the system. Any questions about this construction before I show you what use it is?
A question, I guess, about the interpretation. If I look at the equation for the probability of m lambda, L in that equation looks more like an effective Hamiltonian than a free energy. And I guess I interpret the minimization of L as if you're finding the most likely state. So am I just overthinking the terms, or why do we refer to L as a free energy and not effective?
Because Landau called it a free energy in 1938 before he understood what he was doing.
I see. So really, so the coarse-grained free energy would be the log of that functional integral, whatever. But really, we're working with the effective Hamiltonian.
This is an effective Hamiltonian. It's a coarse-grained free energy. That's our modern understanding. We didn't really understand that until we started thinking about the normalization group and so on.
I see.
Okay. I see. All right. So let's just very quickly talk about what use this is. So I'm going to do what I'd like to do is do this, take a picture, save me drawing this. So why don't I do that? Am I smart enough to be able to do this? Wait, what is that thing? Oh, it's my finger. Huh. Okay, there we go. All right. There we go. Okay, so there we are. Let's save me drawing it. So now let's talk about this. What we have to do is minimize this free energy for different fields and different temperatures. So here I've drawn the curve. Here's the curve, and you can see that this little dot tells you where the minimum is. So here, here. And h is equal to 0. This is the interesting case. And t is greater than tc, it just looks like a quadratic plus a quartic. So it goes like this. So the minimum is at the origin. When t is equal to tc, the quadratic term is gone, so it's just L is equal to e to the 4th. So it looks like this. And when t is less than tc, it looks like this. It's got a double well potential, and so there's two degenerate minima. The system has spontaneous symmetry breaking. It can either be in this well or in this well. And then if I have H greater than 0, I get behavior that looks like this. And if I this describes the first order transition. So this simple description tells you all the phenomena that we associate with continuous phase transitions. Okay, so any questions about that?
Why it should be even when temperature is below freezing?
If H is equal to 0, why not?
Like the temperature, like the older states. In that case,
Once you're in this state, remember this is the free energy for the whole system.
yeah,
Once you're in this state, the ergodicity is broken.
yeah,
And then you're now going to be looking at just fluctuations around this thing.
yeah.
So it does in the same way that the overall Hamiltonian is symmetric, but once you're in the ordered phase, then you're just stuck in one of these potential wells. So remember, this is telling you the expected value of the order parameter. It can either be this value or this one or the other, not both. So in that sense, it's broken the symmetry, it's no longer even. Did I answer your question?
Yeah, because like when we construct this free energy, we just believe it to be even no matter what state it is.
Just like it was, so just like when we talked about in last quarter, the ergodicity breaking,
Yeah.
Same thing is true here.
Yeah, even if it's like ergodicity is broken, we still believe it's like in total it's symmetric.
Just like in the Ising one. Same thing. Okay, so the only thing that happens is the probability distribution of this change. So for example, if you took H is greater than 0, T is less than Tc, so you find it in this minimum here. There's only one minimum. Now I take the limit, H goes to 0. So this one goes down and this one goes up and eventually becomes equal to this. So the limiting process as H tends to 0 from above, there will always be one state that is singled out, just like we talked about last week. Remember, we talked about how one state is exponentially magnified when we're below the critical point. So that's what's happening in this picture here. H is greater than 0, there's only one state. H is going to 0 from above, there's still only one state. But the state you get is epsilon close to this state here. And if I had H going to 0 from below, I would have singled out this state, and I would have, in the limit H goes to 0, T less than Tc, I would have selected this state over here. Is it clear?
Yeah.
Great. Okay, so now let us do, now let us add space. Okay. So that was point 10. So now point 11. Let's add space. Okay, so how do we add space? Well, so let's think about it like this. If I write down the Landau free energy, it's now going to be an integral over space of what? Well, I've got my Landau free energy density that I just worked out, and that's this quartic function of eta. But now I'm going to make eta goes to a function of space. So what you might say is, well, I just take this function that I've already got, the one over here, and I just make eta be eta of r. And then I don't multiply by the volume to get the full free energy. What I do is I integrate over it. Okay? So that's fine, but it's wrong. And the reason it's wrong is because the real physical system has this nearest neighbor coupling between the spins. And what that means is that if I have spins that are wildly different next to each other, that raises the energy. So there needs to be a term in the free energy that penalizes spatial gradients. Remember, in equilibrium, we know that the system will be spatially uniform. So what we need is a term that penalizes spatial gradients. And we need to figure out what that term is. So why do we need that? Why do we need this term? We need this term so that in equilibrium, eta of r is a constant. But I can raise the raise the energy of the system by having a spatial gradient. So spatial variation costs energy. So let's use phenomenology to work out what this term must look like. Now, last quarter I derived it. So let's use from the microscopics, but let's use phenomenology. So this extra term, where does it come from? It has to have spatial gradients. So it's got to be something like grad eta, but it's also got to be translationally invariant. Well, this is translationally invariant. It's also got to be rotationally symmetric. It's got to be analytic. And we want it to be low order in eta. So it's going to involve spatial gradients, rotationally symmetric, analytic, and lowest order in eta. So the lowest order term that you can write down is this term must be something like grad eta of r squared. Oh, the other thing I didn't mention is got to be a scalar, because the free energy is a scalar. So I've got a vector here, grad eta. The only way I can make a scalar out of it is take its dot product with itself. So I have grad eta squared. That is the lowest order term I can write down in spatial gradients. It's quadratic order in eta. So this is the lowest order term. It's analytic, rotationally symmetric. We're happy. So if you think about this in K space, in momentum space, or in wave number space, the lowest order gradient term means looking at small k. It means that we're looking at the long wavelength variations of the order parameter. So our interpretation long wavelength variations of the order parameter. And so our final functional form then is that the Landau free energy is the integral over the space of a term that's proportional to this, what I'll call the coefficient gamma. So half gamma grad eta squared plus then the thing I had before, the uniform part of the free energy density, eta, like so. And that is my Landau free energy in its full generality.
Wouldn't the Laplacian of eta be lower order in eta?
Well, if I differentiated that, what would that give me for the equation of motion? So now let's ask, so remember we need a term that has to be quadratic in eta, so that when we differentiate dl by d eta, we get something that is linear.
I see. That would break the
Z2 symmetry.
Okay, so we derived this last quarter for those of you who took that class, but now you can see that it was inevitable. Okay, so let's see what I want to do next. So this is the form of the free energy, and this applies to any system that has this Z2 symmetry. So what I want to do now is I want to now show you the same thing for systems that have continuous symmetry. Okay, so next thing is now we're going to generalize this to a system with continuous symmetry. So let's go and do that. So what we're going to do is we're going to follow 11.1 in my RG book. So what we're going to do now, we started off with our SI, and now we're going to replace this SI by a vector. So now we have S at each site. SI is now S1, S2, S3, up to Sn. That's site I. So now I have an n component vector here at every given site, and n does not necessarily need to be the spatial dimension. So that's the generalization of the spins. I happen to like using S for order parameter. So what I'm going to do now is I'm going to still use the symbol S for eta, the coarse-grained version. So don't get confused about that. So that means that where I had eta of r just a few minutes ago, now we're going to have a vector S as a function of r that looks like this. So now what we have to do is we have to construct the Landau free energy. That's going to be a function now of this vector order parameter. L is a scalar quantity. This is a vector. So we have to build this up. Is a sum of terms that are scalars. They have to be scalars in terms of this order parameter. So we have to construct scalars, and those scalars have to satisfy all the conditions that we just talked about. So we're going to use the symmetries, we're going to use the analyticity, all of those things. So let's just write down straight away what scalars we can come up with. Well, if I've got a vector S, I can construct a scalar which looks just like the dot product. So I can make a vector which I'll call S squared. And what do I do for that? I take the coefficients, the components rather, S alpha of R, and I dot them with themselves, and then I sum from alpha equals 1 to n. So that's the magnitude squared of this vector. So that's called S squared, and that's a scalar. I can make another scalar which is s to the fourth. And all I do is take s squared and then square that. So that's pretty easy. And then the only other thing that I have to do is I have to construct the gradient term. So how do I write down a gradient term? Well, I'm going to write that in the following way. So what I can do is I can take each spin component, ds alpha, as a function of r. I can differentiate it with respect to, let's say, a Cartesian component of my d-dimensional space, so xi, like that. I need to square it for the reasons that we did before. So I'm now going to square this. And then I'm going to sum over the indices alpha equals 1 to n. That's summing over all the n components of the order parameter. And then I need to sum over the spatial indices, which are represented by I equals 1 to d. So this sum here is summing over x, y, and z, etc. And this one here is summing over the n components of s. So that is a way to generalize the gradient. Okay, so let's now that we've done this, let's have a look at what L looks like. Okay, so what does L look like? When there are no spatial gradients. So the answer is, take a picture from my book. So let's do that. Okay, I need another hand. Okay, can somebody hold this flat, please? Thank you. Great. Thank you. All right. So there we go. Okay, now this is super cool. This is the most important picture in the whole course. Okay, why? Why is this important? So let's make some comments. So the first thing is, let's have a look at the minimum. So I'm writing down. So this V of s is the homogeneous part of the free energy. So it's going to look like half r naught s squared plus 1/4 u naught s to the fourth, and r naught is positive, meaning t is greater than tc. R naught is negative when t is less than tc. So I've used different names for these coefficients than I used before, but it's just what I call A and B. Okay, so that's what I have. So on the left here, this is what happens when R is greater than 0. And you can see that the energy, instead of it just being a parabola, or some quartic function just going like that, it's now a surface of rotation. But still it has its minimum at 0. Now, When I look at below TC, so I set this R naught less than 0. So now, previously we had this double well potential like this. But now we've got this thing as a vector. Here, in this picture here, I'm drawing this for the n equals 2 ON model. I think I mentioned this last time. This model is called the ON model because it is symmetrical under rotations of the vectors. Because you can see we've constructed this in terms of s squared, which is the magnitude of the order parameter. So it's invariant under rotations in the spin space. So now what you see is that when n is equal to 2, so here's S1, here is S2, and now instead of having just 2 minima, now my minima are any states that lie on the bottom of this wine bottle here. If you look at a bottle of wine, it will look something like this bottom here, and you can see that the system can sit in any of these states along here. It doesn't have a discrete set of states, it has a continuum. So the important thing is that for r is greater than 0, or t greater than tc, there is one minimum. And s is equal to 0, but for t less than tc, there's an infinite number of minima. And we can actually calculate it what it is, because V of S is just given by this. So if I say, well, the minimum is given by dV by ds alpha is equal to 0 for all alpha, then what do I get? Well, what I get is that S squared is equal to minus R naught over U naught. Okay, just differentiate this and check this. It's just the same thing we had before. So this S squared is the magnitude of this. So the magnitude of this circle around here is given by the square of S1 squared plus S2 squared. So all we know is the magnitude of the order parameter, and its value is anywhere on this circle. So its amplitude is determined, but its phase is indeterminate. So this determines the amplitude but not the phase of the order parameter. This infinite degeneracy is the whole thing, okay? So it's Mr. Higgs died yesterday, Mr. Higgs of the Higgs boson, okay? He got the Nobel Prize for predicting the Higgs boson by reading Phil Anderson's paper and then writing it down in quantum mechanics. And the Higgs boson was an attempt to answer the following question. If I had a system which has a symmetry like this, a continuous symmetry, then you would expect that there are modes that cost no energy to change the direction of your order parameter, because all these states are degenerate. So we'll talk about that next time. This is called Goldstone's theorem. It says that there's an infinite number of degenerate states of the system, and so the degeneracy corresponds to all of these states going on here. It costs no energy to do that. So that means that if I look at the energy spectrum of those states, the energy spectrum has to go to 0 at longer and longer wavelengths. And that's not what you see in nature. There has to be a reason why you get bosons that have a mass. And as you'll see, if you take this theory and then couple it to electricity and magnetism by just adding a gauge potential, then you can generate a massive excitation, even though you would think from this potential that you would have a massless excitation. So we'll talk all about that later. But this property, this continuous degeneracy of the state, is what gives you this whole, controls the excitation spectrum, it controls the topological defects, it controls the behavior in response to electromagnetic fields if the systems are charged. Everything just comes from that one picture. Okay, so with that, we will end today's lecture. Any questions?
So in that case, like the other parameter is like take an average of several vectors in the window.
No, we are averaging over space.
Like
So what we're doing? Do you mean what do we do when S is a function of R?
I mean like in a close-grained case, what do we do to the string so that we get all the parameters?
We average each component, and then we build the components of the course string model.
So if we average this, what should be like a vector because SI is a vector in this case.
It'll be like the coarse grained thing will be a vector. Exactly. That's right. Right. This S is a vector. You see, it has two components, S1 and S2.
Oh, so S here is a component of this vector.
Yes, it's the S1, S2. It's these components up here. That's how the ON model, right? So n is equal to 2. So S is just S1 and S2. So they're the components in spin space, not in physical space. Like we talked about in last one.
And coarse grain, then you keep them independent.
Yep. So you're going to, the way you would do it, you construct this thing, you take the Fourier transform, you look at the variables, you look at the small k limit, you build it up there. But you've still got the coarse grain vector that is very slowly in space. And that's what the order parameter does in the superfluid or in the superconductor, or in the liquid crystal, or in the electroweak theory of the standard model, and so on. Okay, so right. So I will put the notes and the videos of the lectures online on Teams, and I think I've taught you enough that I can give you a homework sheet. So let me turn off Zoom.